here's another interesting class of automorphism groups. We have automorphism group for Z mod n, the modular integers with n elements, where n is greater than or equal to 3. If we have n equal to 1 or 2, the automorphism group's trivial, so we'll set that aside. Now, because our group is abelian, there are no inner automorphisms. So if we use conjugation, the only automorphism we get is the identity map. That means all the automorphisms are outer, which means we need to do some work to find them. Now, let's recall definition of automorphism. So, an automorphism is just an isomorphism from our group back into itself. So here, we'll have pi going from Z mod n to Z mod n. To be an isomorphism means pi is a bijection, so 1 to 1 onto, and pi is a homomorphism. Our operation is addition, so that says pi of j plus k equals pi of j plus pi of k. Now, Z mod n is cyclic, it's generated by the element 1, so any homomorphism is going to be determined by pi of 1. Now, that means all homomorphisms of Z mod n are in the form pi sub m on k is just equal to m times k, where m is between 0 and n minus 1, including the 0. So we have n of these. Now, for the homomorphism property, there's not much to check there. We just check that m times j plus k equals m times j plus m times k. And that makes sense when we're working in Z mod n. Now, that means the question is, when is pi sub m a bijection? Okay, for here, we can exclude 0. Okay, if we send 1 to 0, everything goes to 0. So that's clearly not going to be a bijection. If I let m be equal to 1, we have the identity map, and we already know that that is a bijection. So we'll just have m greater than 1 for the argument. Answer, greatest common divisor of m and n is equal to 1. So we have that pi sub m is a homomorphism. Recall, if I want to check for the 1-to-1 property, that's equivalent to checking that the kernel of pi sub m is just the identity element. And in this case, that's 0. Because Z mod n is finite, checking 1-to-1 is enough. Now, recall, kernel of pi sub m, that's going to be set of all k and Z mod n, such that m times k is equal to 0. So that's what we get when we apply pi sub m. Now, what we want to show, that the kernel of pi sub m is equal to 0, if and only if greatest common divisor of m and n is equal to 1. If we show this direction, so I'll use contradiction. So let's suppose the greatest common divisor of m and n is equal to d greater than 1. So we're assuming the kernel here is equal to 0. Then we could write m as, product of two integers, j times d, n as k times d, where k is between 0 and n. That means if I apply pi sub m to k, then we'll have m times k, but m is equal to j times d. I push the d over to the k, and that becomes n. So this is going to be equal to 0. So that means we actually have an element in the kernel, so we can't have the kernel equal to only 0. For the other direction, let's suppose greatest common divisor of m and n is equal to 1. I want to check that the kernel is only 0. So let's suppose pi sub m of k is equal to mk by definition is equal to 0. Now, in the integers, what this says is that m times k is equal to a multiple of n, say j times n. Now, that means n is going to divide m times k, but because the greatest common divisor is equal to 1, that's going to force n to divide k itself. So in Z mod n, k is equal to 0. So that gives our other direction. Seeing is believing. So let's consider the following two homomorphisms. We have Z8 mapping back to itself. If we consider pi 3, so greatest common divisor of 3 and 8 is 1, so we expect an isomorphism. We're going to take each of these numbers, multiply by 3, and then reduce mod 8. So we see that 0 only occurs once, and we can check directly that we have a bijection. So that checks out. Then I can consider pi 6. Greatest common divisor of 6 and 8 is 2. We multiply each of these numbers by 6, reduce modulo 8. Then we notice we don't have a bijection anymore. So we have 0 occurring twice, so our kernel has 2 elements in it. Now, that gives a description of Aut Zn. So Aut Zn is given by all homomorphisms pi sub m, where the greatest common divisor of m and n is equal to 1. And then m is just being chosen between 1 and n, including the 1 but not including the n. Now, that's a group. So note the way we multiply elements, pi m times pi l is pi ml. Okay, because of this, our group is abelian. The identity element is going to be pi 1. And then when we get to inverses, it's not clear what we have for an answer here. So the idea is we ask if the greatest common divisor of m and n is equal to 1, is there a k such that k times n is equal to 1 in Z mod n? For the answer here, we go to a result from the integers. So if we have greatest common divisor of m and n equal to 1, we can find two other integers, r and s, such that r times n plus s times n is equal to 1. Then, if we go to Z mod n, okay, s times n is going to go to 0, so I would have r times m equal to 1, and that r is equal to the k that we're looking for. So the answer is yes, we can find an inverse, but we actually have to go and find it. It's not a cookbook recipe. Now, we shift the focus from Aut Zn to the integers that give us the bijections. So we have a definition. We'll call Z mod n star set of all m in Z mod n such that greatest common divisor of m and n is equal to 1. Okay? Another way to say that is that m and n are relatively prime. Now, we've just seen that this is a group. Terminology, I'll call Z mod n star the group of units in Z mod n. Where this comes from, if R is a ring, so that'll be a set with an addition and a multiplication, which satisfy compatibility conditions. Then the units are going to be the set of all elements in the ring, such that there exists a multiplicative inverse. So we're just looking for all elements in Z mod n, which have a multiplicative inverse. Now, interesting problem. Describe the isomorphism classes for Z mod n star. This we can do, but the techniques we use go hand in hand with the proof of the fundamental theorem of finite abelian groups, so we save it for much later. Now, examples. So remember the problem we're interested in. Let's find the inverses for every element we put on the board. If we take Z mod 8 star, okay, we'll have 1, 3, 5, and 7. This group has order 4. We know the isomorphism classes for abelian groups of order 4 are Z mod 4 or Z mod 2 cross Z mod 2. If I square each element, okay, so 9 squared is equal to 1, 5 squared, 25 goes to 1, 7 squared, 49 goes to 1. So every element has order 2 or 1. So we know we have Z mod 2 cross Z mod 2. Note, every element is its own inverse. For Z mod 3 star, we have only 2 elements, 1 and 2. If I take 2 and square it, we get 4, which goes to 1. So it's its own inverse also. So Z mod 2. For Z mod 5 star, Okay, we have 1, 2, 3, 4. If I take 2, I square it, I get a 4. Cube it, I get a 3. The fourth power, I get a 1. So I have an element of order 4, which means our group is cyclic. So Z mod 4. Note, 2 and 3 are inverse to one another. 2 times 3 is 6, which goes to 1. And 4 is self-inverse. So 4 times 4 is 16, goes to 1. One more, we'll do Z mod 7 star. So we have 1 through 6. If I take 3, that's going to generate the group. So we're going to have Z mod 6 for the isomorphism class. Note, 2 and 4 are inverse to one another. Okay, 2 times 4 is 8, which is 1. 3 and 5 are inverse to one another. 3 times 5 is 15, goes to 1. 6 is self-inverse. So 6 squared is 36, goes to 1. Now, why these 3 examples? Well, there's a pattern here. So the theorem, which we don't have the techniques for yet, if P is a prime, then the group of units for Z mod P is isomorphic to a cyclic group of order P minus 1. Up to now, we've studied groups for their own sake, but originally groups were used as a device to study zeros of polynomials. That's Galois theory. From there, whenever symmetries arise, we can apply group theory, and groups show up everywhere. Here, we want to apply group theory to get a result from number theory. Now, before we can do that, I have to take the language of modular integers and rewrite things as statements about integers. So definition, if we have A and B integers, we'll have an equivalence relation. A is congruent to B mod n, if and only if n divides A minus B. So that just says A and B will have the same remainder when we divide by n. Let's look at the equations. So we have A as a multiple of n plus remainder j. I can write B as multiple of n plus remainder j. And if we take the difference, the j's go away, and we have A minus B is a multiple of n. So A minus B is an element of n times z, or A is in B plus nz. So in the language of quotient groups, we're saying that A and B are in the same coset by n times z. So that says when I consider an element of Z mod n, okay, recall, that's a coset by subgroup nz. All the elements in that coset have the same remainder upon division by n. Now, I need a definition. We have the Euler totient function. So this is going to be defined on positive integers. What we have, totient function on n, just given as the number of elements, m, that are relatively prime to n, and between 1 and n, including 1. So this should be familiar. That is the order of Z mod n star. Now, we have a corollary to Lagrange's theorem. If I have G a finite group, then the order of any element in the group divides the order of the group itself. So that implies that if I take any element x, raise it to the order of G, we get the identity element. Now, if I apply that to Z mod n star, okay, we know the order of the group is the totient function on n. So I have, for any element x in the group of units of Z mod n, x to the totient function on n is equal to 1 in Z mod n. If we rephrase in terms of integers, we have the following result of Euler. If k and n are relatively prime, then k to the totient function on n is congruent to 1 mod n. Or n divides k to the totient function on n minus 1. If we consider the special case where n is a prime p, the only divisors of p are 1 and p, so the totient function of p is p minus 1. And then we have two cases. If K is not a multiple of P, and K and P are relatively prime, and Euler's result applies. So we have that K to the P minus 1 is congruent to 1 mod P. Or P divides K to the P minus 1 minus 1. In the other case, if K is a multiple of P, then P divides K. P will also divide K times any other integer. So let's multiply K by K to the P minus 1 minus 1. This gives our main result, Fermat's little theorem. If P is a prime, then for all K in the integers, K to the P is congruent to K mod P. Equivalently, P divides K to the P minus K. Note, we're not likely to stumble upon this result just experimenting with integers. Now, let's check. So first we'll check Euler. So if I choose n equal to 10, group of units in Z mod 10, we have 4 elements, 1, 3, 7, and 9. So the totient function of 10 is equal to 4. I have to take numbers that are relatively prime to 10. So if I take 3 to the 4 minus 1, we get 80. 10 divides 80, so that checks. If I take 7 to the 4 minus 1, we get 2400. 10 divides 2400, so that checks. If I try a number that's not relatively prime, so say 2, 2 to the 4 minus 1 gives me 15. 10 does not divide 15. So we definitely need the relatively prime condition. If we go to Fermat, okay, there's no condition at all on the integer that we use. So let's try P equal to 5. If I take 2, 2 to the 5th minus 2 gives me 30. 5 divides 30. We try 3. 3 to the 5th minus 3 is 240. 5 divides that. We try 7. 7 to the 5th minus 7 gives me 16,800. And 5 divides that. Okay, you'll also note 10 is going to divide all of these, and that's just because we're taking a difference of 2 evens or 2 odds.